Imagine, for a second, stepping into a vast visual memory palace. Every single room holds a different mathematical concept, but today, we're walking straight past the basics and unlocking the vault for the Cambridge IGCSE Additional Mathematics Syllabus 0606. In this explainer, we're going to zero in on exactly how to secure maximum marks for one of the most notoriously tricky topics on the paper, the sum to infinity of a convergent geometric progression. We're going to break down the exact strategies examiners desperately want to see, the sneaky traps they lay out for you, and how to completely bulletproof your working under intense exam pressure. Let's dive right in.
Right off the bat, we need to address a really painful learner mistake. I'm talking about the kind of mistake that literally puts entire grade boundaries at risk during high-stakes exams. You see, most students walk into the exam hall feeling incredibly confident about their algebra. But if you look at Cambridge principal examiner reports, they reveal a fascinating and honestly slightly terrifying trend. Even the top-performing students are losing easy, predictable marks on this specific topic. And get this, it is almost never because they don't know the math. It's all about how they apply it.
So here's the stark reality. You can easily score an absolute 0 on a concept you actually understand perfectly. Crazy, right? Well, principal examiners point out that students fundamentally confuse cause and effect when dealing with infinite series. They just plug numbers into a machine without stopping to prove whether that machine should even be turned on in the first place. You might do a full page of flawless arithmetic, but if your foundational logic is backwards, you get nothing. Absolute 0. Section 1. Unpacking the infinity formula. All right, let's look at the exact wording of your core formula. The sum to infinity equals a, your first term, divided by 1 minus r, the common ratio. But ordinary revision completely fails here because simply memorizing the equation isn't enough to survive Cambridge's tricky applications. The absolute critical condition, the part that trips literally everyone up, is that the absolute value of the common ratio r must be strictly less than 1. If you apply this formula to a sequence that doesn't converge, your mathematical logic breaks down entirely. And that leads right back to that painful 0 we just talked about. See, the Cambridge syllabus demands way more than rote memorization. It clearly states that you have to take this mathematical principle and flawlessly apply it to entirely unfamiliar contexts. The examiners are going to dress this sum to infinity question up. It might look like a physics problem about a bouncing ball, or maybe a geometry problem with shrinking triangles. A top-performing student doesn't panic when the context changes. They exhibit connected conceptual understanding. They see that hidden geometric progression lurking beneath the unfamiliar surface. In just a sec, I'm going to reveal the specific examiner clue that completely changes your answer. But first, you need the operational framework to actually process it without making unforced errors. Think of this as your most important diagnostic tool. Section 2. The procedural framework. Okay. By rigidly following these 5 steps, you completely eliminate careless formatting errors. First, deconstruct the question to identify the key elements. Second, extract the relevant data. Go find your A and your R. Third, select the analytical framework, meaning confirm it's actually a convergent series. Fourth, execute your analysis with super clear step-by-step working. And finally, present the final answer with the correct terminology and format. Do not skip a single one of these. This sequence is exactly what separates the elite candidates from everyone else. Now, the crucial point here is that this exact procedural sequence guarantees you capitalize on what we call the method mark strategy. This is a total game changer. The Cambridge mark scheme is explicitly designed to reward your mathematical reasoning. By showing your clear step-by-step working, you can actually save your grade, even if your final calculation goes totally wrong because of a silly, panic-induced calculator typo. You're basically buying insurance for your grade through your methodology. Just look at how brilliantly this illustrates the difference. A flawed approach means rushing straight to a final calculation with 0 working shown. Make one slip, you lose everything. Now look at an improved top band response, explicitly extracting the A and R variables, writing them down with crystal clear notation, and justifying the steps. By doing this, you're communicating directly to the examiner, basically saying, hey, I know exactly what I'm doing. Section 3. Top 3 examiner warnings. Listen up, because principal examiners explicitly call out these 3 exact pitfalls. First, that cause and effect confusion we mentioned earlier, using the formula without proving the sequence actually converges. Second, sloppy formatting, forgetting proper headings, annotations, or the right terminology. And third, completely ignoring the specific context of the question. If the question is about meters and your answer is just a raw number without units, or if it just doesn't make logical sense in the real-world context of the problem, you are going to drop marks for sure. To really lock these warnings into your brain, you need a quick memory hack. Take the first letters of those key terms: cause, format, context, or maybe deconstruct, extract, select from our earlier framework, and create a quick first-letter mnemonic right now. By actively building this mental shortcut, you ensure you will never, ever forget to run these checks when you're sweating under intense exam pressure. You've got this. Ultimately, all of this builds into the ultimate problem-solving loop: deconstruct, solve, and evaluate. We've talked plenty about deconstructing and solving, but that third step, evaluation, it is absolutely paramount. Your problem-solving must always end here. You've got to check your final answer for reasonableness. I mean, does a sum to infinity of 500 really make sense if the first term is only 2? You must justify your decisions with solid evidence. This kind of evaluative thinking is a higher-order assessment objective that examiners desperately want to see on your paper.
Section 4. Unlocking the next level.
Okay, so you now possess the core procedural framework, the formulas, and the examiner warnings. But there's still one final locked room in our memory palace. Imagine this scenario. You execute a flawless calculation for the sum to infinity. Your algebra is absolutely perfect, your method marks are totally secured, but you still drop the final marks. Why? Because you missed a critical analytical layer. You failed to spot a hidden contextual error in how the question was framed. How on earth do you catch something that isn't just about the numbers, but about the deeply embedded assumptions in the question itself? To avoid falling into that trap, you have to master those higher-order skills. The top-scoring candidates, they don't just solve. They demonstrate evaluative thinking by questioning the given assumptions, comparing different mathematical approaches, and justifying their final recommendations. This framework comprises descriptive, analytical, and evaluative levels. And making that massive leap from purely descriptive to highly evaluative, that is exactly what secures the A-star. So here is the question that leaves our current room locked. Are you ready to master the exact analytical skills that separate the good candidates from the elite ones? Because infinity isn't just a number. It's a concept that requires a real strategy to conquer. To secure those elite grades, your mandatory next step is to dive right into our subsequent explainer. We're going to cover the complete top-band evaluation framework for syllabus 0606. I will see you there.